You bought
Hi there, my name's Jared
of,
Keene,
uh,
and this
color
is the
sensor
embedded group number
breakouts.
1.
Do those plug in?
Let's go ahead and
Are they
introduce
soldered
ourselves,
down
and
and,
we'll talk a
and
little bit about
expendable
our
or
project.
what? I'm John.
I'm Austin. And I'm Chris.
I mean, do you need them?
Just to give you guys an overview of what
No,
we did,
no,
let's
no,
go
I
over
mean,
to Embedded Trade
some
Town and take a
things
look
are
at our project.
consumables. Right. Yeah, just
Hi, I'm Chris, and this is our train embedded town. Our project was to route multiple trains around this track given user-specified input. The point of the project is to route a train along a path generated by the user and avoid collisions. Collisions are very bad. Two trains colliding is not a good thing. When they go around the track, the user specifies whether they'd like the path to be repeating or whether they'd like to be looping. This is done by these sensors positioned strategically around the track to tell our microcontrollers where they are. For this project, we use 3 microcontrollers, an ARM and 2 PICs. They communicate by both the sensors, and the LocoNet is how we communicate with the trains and send out commands to throw switches, such as these, and train speeds.
Hi, my name is Jared Keene, and I was in charge of the hardware and the custom pick board for our embedded project. Why don't we go over to the pick board and let's take a look at it. Alright, so this is our custom pick board here. We implemented a PIC 18 F45J10 processor as well as an MCP 23018 I2C I/O module. Now, these two components right here communicate via I2C, where the PIC 45J10 is the master and the 23018 is the slave. They're connected via a clock and a data output line, and that's how they pass data between each other. Now, what we used as sensors were Hall effect sensors, which we'll go over later. But all of the sensors are connected to this I/O module, and whenever we get a value change on our sensors, it generates an interrupt. Now, this interrupt is attached to an external interrupt pin on the F45J10, and when it gets its interrupt, it reads the values from the sensors and is able to send those values via another I2C port to our ARM processor, which we'll talk about later. In addition to that, we have an I2C buffer right here, which drops down our I2C voltage from 5 volts to 3.3 to allow for integration with the 45J10. Alright, if we go up to the train board, we can take a look at our sensor network. So this is our little embedded train town here with our sensor network. As you can see, there's a series of sensors mounted up on wooden blocks all around the track. And basically what the sensors are used for is detecting when a train passes underneath them. Now, the sensors we used here are Hall effect sensors, and basically what we do is we attach a magnet to the top of our trains, and when the magnet passes underneath our Hall effect sensors, it trips the sensor and it changes the value on the input pins to the PCB board that we looked at earlier. So whenever one of our sensor values gets tripped, our ARM is able to tell that a train passed into a new section, and we can route that information to our pathfinding algorithm, which we'll talk about later as well, and let the trains know where they need to go. So next we're going to talk to Jonathan over here, and he's going to tell us about how our trains get commands and how information gets sent from the track to our ARM processor.
So we've been talking about something called LocoNet a little bit, and what that is a protocol for communicating with the trains. LocoNet messages are distributed to all devices on the tracks. The track is the bus, the physical means of communicating with the trains, and the LocoNet distributes messages to everything, but only the devices that are addressed in each message react. For instance, this train's address is 3, so this is the DCS50, which controls the train. So if if I select the train and then set forward, the train will move, but nothing else on the track reacts. And that's how LocoNet works. And there's 2 plugs in the back of this. They're phone line cords with 6 wires. And so we plug into the second port and use our PIC microcontroller to send our own messages to control the trains and switches on this track. And we'll move to explaining how that PIC works now. This is the board we use to communicate to LocoNet. It has an 8-bit PIC on it, and what it does is it receives instructions from the Kyle board over I2C, or the train bus, which is, we use a ribbon cable to connect our devices to. And then it sends that message through message queues on the PIC out to UART, and UART output and the receive pins are here, which connect to this LocoNet conversion board, and that just sends the messages to LocoNet. We had to get the baud rate right for this to work, and that's in the LocoNet spec. But this was a major part of the project because it allowed us to communicate and receive data.
I am Chris, and I have been charged with coding the ARM microcontroller. The ARM microcontroller is a microcontroller that is operated on the Kyle development board that is running a version of FreeRTOS. FreeRTOS stands for Free Real-Time Operating System. On the ARM, I have spawned 2 threads for our project, an algorithm thread and the I2C temp thread. The I2C temp thread is in charge of talking to both PIC microcontrollers over the I2C bus. The algorithm thread and the I2C thread are very important in communication. So we use two message queues that communicate between them. They are both one way, and one goes to the algorithm thread and one goes to the I2C temp thread. The algorithm, or the message queue that goes from the algorithm to the temp thread, is in charge of only sending out LocoNet commands. Through the LocoNet commands, the I2C temp thread converts them to actual LocoNet messages and sends them over the I2C thread to the PIC that is in charge of talking to the LocoNet. The I2C temp thread then also reads in sensor information from our track, puts that into a message queue, and the algorithm reads that. Through that information, it does its magic, its logic, and updates its own internal state variables. These state variables are what control the messages sent to the I2C temp thread. The current algorithm uses a two-phased approach. The first phase takes in the user-specified train points that a user wants the train to travel around and plugs it into the Dijkstra's graphical search algorithm that is currently implemented on the ARM itself. This algorithm generates a shortest path for each train to follow along our track. Now, this is non-transferable to other tracks for the fact that every vector on our track has to be hard-coded in order for this to work. Once you can actually code all the vectors into the algorithm, it will work on any other track, but it's non-plug and play. You have to actually code it yourself. The second phase takes in the sensor information from the I2C temp thread. This thread takes in the sensor information, updates the state variables within the algorithm itself. Based off these variables, if it needs to, it sends out a command over to the I2C temp thread. While this is going on, it is currently run by just blocked message queues from the temp thread itself. So when there is no relevant sensor information, this thread is actually paused.
The original design included a web server to accept user input for train routes. While this was completed, it was not integrated into the final project because of memory concerns. We did, however, implement a train location API using the LCD. This is designed so that any programmer can easily see train information by adding a few files to the project. The location API is broken up into two separate threads. The main API accepts the current location of the train, plus the next location and the following location after that. It needs the next nodes to determine which direction the train is going in. For every node, the API will determine two arrays that are either leading in or leading out of it. If the next node matches one of these two arrays, then it knows that the array is in the forward direction and the other is in the reverse direction. Then it repeats this process to find the next nodes after the next. Once the API thread determines which nodes lead into it, which nodes are next, and which nodes come after that, the thread sends this information over to the LCD thread in a string format. Then the LCD thread puts each value into the appropriate spot on the LCD. Plus, if there are too many branching nodes for a given spot, it will display an M for multiple. This is an example of the train location API. The timing of the API thread with the other threads causes some problems. But, as you can see here, the main I2C thread passes over the correct values for the train location, and it displays them here on the screen. Here are the previous nodes, 5 and 6. This is the current node, and these are the nodes that it can enter, and these are the following nodes after that.
As you can see in this video, the train is routed along a hard-coded route. This is because we did not have a working GUI. We also only got our project to work with one train. At this node, the second to last turnout is switched. At this node, the last turnout is switched. At this node, we stop the train.
Some difficulties we encountered in this program were, one, we were unable to test multiple trains working on the track itself, so the algorithm right now, while taking into account collisions, does not currently run two trains. Also, the specification of the project was to continually run the trains in either looping or reversing orders. This current implementation actually stops the trains at its destination and does not loop them. Another thing with the algorithm thread is that we were unable to get the web server interface working, so we have no specified user input. At the beginning of the algorithm thread, before the Dijkstra's algorithm, you actually have to input the points you want it to go at the beginning, so they're hard-coded.
Some difficulties related to controlling the trains include collision detection, which it's not in the same sense as actual physical train collisions. We are talking about collisions on the LocoNet bus, and without proper collision detection, sending messages is unreliable, and therefore a lot of our messages sent to the trains were not received by the LocoNet throttle control, and therefore we were unable to reliably control trains. Another issue with that is flow control, which alerts the arm when a message has been sent successfully. So since we weren't able to get collision detection working, flow control didn't work either, because it was kind of irrelevant. If you can't verify that the messages were sent, then there's no point in faking a verification message to send back to the Kyle development board. And then the last thing, which kind of is included in collision detection, is we weren't able to figure out how to acquire the trains properly from the DCS-50 throttle, and therefore that device would send out messages periodically to the trains, and this would cause our instructions to be null, because we would send an instruction and then it would stop the train. So those three things gave us quite a bit of issues in the final demo of the project.